Lecture 8.3, Relative Rates of Growth. The function y equals e to the x grows very fast. We could graph it on the chalkboard if we had an old-fashioned chalkboard. It would look like this. If x is 3 inches, y is about 20 inches. At x equals 10 inches, y is 1/3 of a mile. At x equals 44 inches, y equals 2 million light years. We have gone less than halfway across the board horizontally, and already the y value would reach the Andromeda galaxy. At 64 inches, the y value would be at the edge of the known universe, 13 billion light years. The function y equals ln x grows very slowly. Once again, we graph it on the chalkboard. It looks like this. We would have to move 2.6 miles to the right before the line moves a foot above the x-axis. By the time we reach the edge of the universe again, 13 billion light years, the chalk line will only have reached 64 inches. The function y equals ln x increases everywhere, even though it increases extremely slowly. Definitions: faster, slower, same rate growth as x approaches infinity. Let f of x and g of x be positive for x sufficiently large. 1. F grows faster than g and g grows slower than f as x approaches infinity if the limit as x approaches infinity, f of x over g of x equals infinity. Or the limit as x goes to infinity of g of x over f of x equals 0. 2. F and g grow at the same rate as x approaches infinity if the limit as x goes to infinity of f of x over g of x equals L, not equal to 0. That is, equals to a non-zero constant. Warning! 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 Please temporarily suspend your common sense. According to this definition, y equals 2x does not grow faster than y equals x. There's y equals x, y equals 2x. The limit as x goes to infinity of 2x over x equals the limit as x goes to infinity of 2, which is 2. Since this is a finite non-zero limit, the functions grow at the same rate. The book says that f grows faster than g means that for large x values, g is negligible compared to f. Grows faster is not the same as has a steeper slope. Which grows faster, e to the x or x squared? We take the limit as x goes to infinity, e to the x over x squared, which approaches infinity over infinity. This is indeterminate, so we apply L'Hopital's rule. Now we have the limit as x goes to infinity of e to the x over 2x. Still infinity over infinity. Still indeterminate. Applying L'Hopital one more time, we have the limit as x goes to infinity, e to the x over 2, which is infinity. Therefore, e to the x grows faster than x squared. We can confirm this graphically. There's the graph y equals e to the x over x squared. Growing at the same rate is transitive. In other words, if two functions grow at the same rate as a third function, then the first two functions grow at the same rate. Example 4. Show that f of x equals radical x squared plus 5 and g of x equals 2 radical x minus 1 quantity squared grow at the same rate as x approaches infinity. Let h of x equal x. The limit as x goes to infinity of radical x squared plus 5 over x equals the limit as h goes to infinity of radical x squared plus 5 over radical x squared. Remember, x is positive, so radical x squared is x. This gives us the limit as x goes to infinity of radical x squared over x squared plus 5 over x squared, which is the limit as x goes to infinity of radical 1 plus 5 over x squared. And as x goes to infinity, this term approaches 0, so our limit is 1. Now, if we compare 2 radical x minus 1 quantity squared with x, we can take the limit as x goes to infinity of 2 radical x minus 1 quantity squared over x, which is the limit as x goes to infinity of 2 radical x minus 1 quantity squared over radical x squared. We can separate this fraction. Cross out the radical x's on the left, and the second term goes to 0 as x approaches infinity. So we get 4. The limit as x goes to infinity of f over g is equal to the limit as x goes to infinity of f over h times h over g, which is 1 times 1/4, or 1/4. F and g grow at the same rate. Order and O notation. Definition: f of smaller order than g. Let f and g be positive for x sufficiently large. Then f is of smaller order than g as x approaches infinity if the limit as x approaches infinity, f of x over g of x equals 0. We write f equals OG and say f is little o of g. Saying f equals little o of g is another way to say that f grows slower than g. Now, you might think, if we were to pick a symbol that was the most likely to get confused with a number, a lowercase o would probably be it. But if that's not bad enough, the definition of f of at most the order of g is this. Let f and g be positive for x sufficiently large. Then f is at most the order of g as x approaches infinity if there is a positive integer m for which f of x over g of x is less than or equal to m for x sufficiently large. We write f equals big O of g. So we have to be able to tell that uppercase O from a lowercase o. Saying f equals big O of g is another way to say that f grows no faster than g.